Here's a process where we're using a force to form a component. It's the force of gravity. You can't see a force, but you can see its effects. In engineering, we use the effects of forces all the time. This pilot is using the downward force from the nozzle to lift his aircraft in a vertical takeoff. He knows the direction of the force, even though he can't see it. Every force has a direction. The flight path of this Sea Dart missile depends on the angle of firing. The effect of a force depends on the angle at which it's applied. You can add forces for a bigger effect. For instance, on an aircraft carrier, a jet fighter only has a very short distance for takeoff. It takes the combined force of the catapult and the jet engine to give it enough acceleration. You can subtract forces too. The tension in this cable pulling in the opposite direction draws the jet to a swift halt. By adding and subtracting forces, the Harrier pilot can balance them out, making the aircraft hover. In a lift, you have the force of gravity acting downwards on the men, the cage, and these weights. The tension in the cables pulls upwards with the force of the motor. All these forces combine to keep the lift moving steadily. This device on the top of a high crane measures the speed of the wind. Every force has a size. Wind speed is an indication of wind force. This crane is designed to withstand gales of up to 140 kilometers an hour, but if the wind speed exceeds half that much, it's unsafe for the driver and work must stop. Here's an experiment we've set up to examine the forces involved in slinging. If we measure the tension in the slings, we find it's 20 newtons in each, a total of 40. The same as the load. We've now changed the angle between the slings. The load is still the same. But the tension's changed. It's gone up to 25 newtons. If we increase the angle still further, the tension goes up even more, to 30 newtons in each sling, though the load has never changed. That's why the angle is critical in slinging. The greater it is, the higher the tension in the slings. If you're not careful, you could exceed the safe working load. When you tighten up a nut, you're applying a force. Usually you start by doing it up finger tight, but you always have to finish the job off with some sort of tool. A Tommy bar or a torque wrench. Only by using some sort of tool can you apply a large enough force to the nut. Applying a spanner to a nut produces a turning effect. Engineers call this turning effect a moment. The turning point is at the centre of the nut. That's the pivot. The spanner provides a lever which enables you to apply a force at a distance from the pivot. By doing this, you can apply a much larger force somewhere else. It's this basic principle which enables one man to lift a lorry more than 10 times his own weight. Let's find out how we can make the best use of a lever. Well, suppose one man can lift this much load. Two men, or twice the force, can lift twice as much. Three times the effort can lift 3 times the load. But it's unusual to increase the effort. There's another way of using a lever. Here's a clue. When you want to apply a really big force to a nut, you choose a spanner with a long arm. When less force or effort is needed, you choose a shorter one. In fact, you can always find a spanner that's the right length for the job. Let's look at some more examples like this. With only one hand, you can apply enough force to wrench out a nail if you use a claw hammer with a handle this long. This mechanic needs only one hand to fit on the tyre, using a lever this long. And what about this? An even longer lever arm. Let's look at that idea in our diagram. Now, instead of a large force, we'll apply a smaller one at twice the distance from the pivot and see how much load it can raise. Now let's see how much we can raise if we make our lever arm 3 times as long. Can you see what's happened? If 3 men can lift this much load with a lever this long, one man can do just as well with a lever 3 times the length. So the turning effect of a force depends on 2 things: the size of the force and the length of the lever. Here we're applying a couple of forces. A tap wrench is another kind of lever, but the pivot is in the centre this time. By using a wrench, we can obtain a big enough force to tap the thread. The same principle applies again. When you want to tap a bigger diameter thread, you use a tap wrench with a longer arm. Tapping a large diameter thread needs a really big force, and we apply forces at both ends of the wrench, both producing a turning effect in the same direction. Now, you may think this is quite a different situation, but look at the way a tower crane is constructed. It has a front jib, a pivot, and a counter jib with a weight on the end. But why do you need the bit at the back? Well, suppose we hung a weight from a bar balanced on a pivot. The weight would tip the bar round in a clockwise direction. And a weight on the other side would tip the bar round in an anti-clockwise direction. Now you can balance everything out by applying a weight at a suitable distance the other side. That's why we need a weight at the back end of a crane. It helps to keep everything in balance. The engineers who design these cranes have many more turning effects to take into account. Without these concrete ballast weights at the base, a crane which runs on rails would topple over. Here's another example with the pivot in the center. The component between the rear wheels of this lorry is called a balancing beam. Its job is to balance out the load between the two axles as the lorry drives over a bumpy surface. It looks complicated, but it's just another kind of lever. And here's another. But what have clamps to do with levers? Well, have you ever thought where the clamping bolt should go when you're restraining a piece of work like this? The nut applies a downward force. The work resists with an upward force. The more it resists, the tighter the work is clamped. Let's simplify the situation. Here's the downward force of the nut. We want the force from the work to be as large as possible. If we move the nut away from the work, how does that affect the size of the resisting force? Is it larger here or here? This dial measures that resisting force. Let's see what happens if we move the nut away from the work. The further away it is, the smaller the resisting force. But as the nut gets nearer the work, the force gets much larger. So to get the maximum clamping force, the bolt should be as close to the work as possible. When you're slinging any load, there's always one point where the whole weight of the load seems to act. Let's see what that means. This bar balances perfectly at its center. It's as if the whole weight of the bar were acting through that point. Now let's try and do the same thing with a bar that's heavier at one end. When we try to balance it at the center, it tips up. The weight of this bar acts through a different balancing point, and it's the balancing point which we call the center of gravity. When you sling any load, it will always settle with its center of gravity directly under the hook. In this case, it's the center of the crankshaft. The slings are arranged to keep it level. Now let's go back to our experiment. We've slung the bar so that it hangs level, and the plumb line shows that the center of gravity is directly beneath the hook. But what happens if we make the bar heavier at one end? The bar tips until the new center of gravity is under the hook, but now the bar is no longer level. Here we're using slings of different lengths, 2 short and 1 long. But why? Like the bar, this assembly is heavier at one end, although this time it's heavier on the right. If we used slings of equal length, it would tend to tip until its center of gravity was directly beneath the hook. By using slings of different lengths, the load hangs level, even though it's heavier at one end. This casting has thrown the faceplate out of balance. But does it matter? Well, let's try running the lathe at a fairly high speed. Well, that's something you should never try. It was out of balance. Let's balance it up. If you have to use a slotted weight, you should never fasten it like this with the open end towards the center. Can you think why? For this particular casting, we found we needed 2 sets of counterweights. What we're doing here is to balance out the weights on both sides of the spindle. Now it's balanced. But this wheel isn't. And that's not too good for the car or the driver. Balancing up a car wheel is very like balancing the faceplate. First, you mount the wheel on a spindle. Then you let it go to see where the extra weight is needed. And just as before, you add on an extra weight to get the wheel in balance. Here's another component that has to rotate at very high speeds. Once again, to test for balance, it's mounted so that it can rotate quite freely. Balance is highly critical here, so it's tested electronically. This meter shows how much the component is out of balance. And a scale tells the operator exactly where. This time, instead of adding weights to the component, the operator will balance it up by removing material. By adjusting the scale, he gets the out of balance point exactly opposite a drill. The precise amount of material is removed. It's a method that gives almost perfect balance.